Unreliable JSON output from a large language model is not a minor parsing issue, it is a critical system vulnerability. When an application receives malformed data, the immediate consequence is a JSON decoder error, halting the data pipeline and requiring immediate exception handling or a costly, time-consuming retry mechanism. Standard prompts like "output the result as JSON" are insufficient because they rely solely on probabilistic text generation, failing to enforce structural integrity at the token level. The system analyst must implement deterministic controls. Our goal is to shift the LLM from being a creative text generator to a reliable data serialization engine, ensuring every output string strictly adheres to a predefined schema for seamless API integration. The first layer of defense is precise prompt engineering using strict delimiters. Define the output boundary using triple backticks or dedicated XML tags, explicitly instructing the model to place the JSON object exclusively within these markers. Crucially, the system prompt must define the required root object and specify data types for every field. For instance, state that user identifier must be a string matching the UUID version 4 pattern, and status must be an enumeration of pending, complete, or failed. This specificity reduces ambiguity. Always include a few-shot example demonstrating the exact structure, including correct nesting and array formatting, reinforcing the required output format. Relying on natural language descriptions is prone to misinterpretation. Instead, inject a formal JSON schema definition directly into the system prompt. This schema must define required properties, data types, and constraints using keywords like type, properties, and required. For complex objects, utilize the .dev section for reusable definitions, improving clarity and reducing prompt length. The instruction must explicitly state, the following JSON object must strictly conform to the provided JSON schema definition. This provides the model with a machine-readable contract, significantly improving compliance compared to simple text instructions.
For models supporting it, such as recent OpenAI or Anthropic versions, the most reliable method is utilizing the native response-format parameter. Setting this parameter to type.json-object forces the model's decoding layer to prioritize tokens that maintain valid JSON syntax throughout the generation process. This mechanism actively prevents common errors like trailing commas, unclosed brackets, or incorrect escaping. This approach bypasses the need for extensive prompt engineering focused purely on syntax, offering the highest performance and reliability ratio for structural compliance. Always verify model documentation for specific implementation details regarding this feature. In Python environments, Pydantic is the essential bridge between application code and LLM output. Define the required data structure using a Pydantic base model. This model automatically generates the necessary JSON schema, which is then injected into the LLM prompt. Upon receiving the LLM output string, the application attempts to parse and validate it against the Pydantic model. Pydantic handles type coercion and raises specific validation exceptions if constraints are violated, providing precise feedback on which field failed validation. This ensures data integrity before the data is committed to any downstream system or database. For mission-critical applications demanding zero parsing failures, explore libraries that enforce grammar at the token level, such as guidance or outlines. These tools modify the sampling process, ensuring that the model can only select tokens that maintain valid JSON syntax according to the defined schema at every step of generation. If the schema requires a closing brace, the model cannot output a comma or a string literal. While computationally more intensive, this method guarantees structural compliance, eliminating the possibility of syntax errors entirely. This is the definitive solution when native API JSON modes are unavailable or insufficient.
Even with robust constraints, occasional malformed output can occur due to model stochasticity. Implement a structured retry mechanism that leverages the LLM itself for correction. If the initial parsing attempt fails, catch the JSON decoder error and feed the raw invalid output string along with the specific error message back to the LLM. The instruction should be, the previous output failed parsing due to this error. Insert error message. Correct the output to strictly adhere to the schema. This self-correction loop minimizes external application logic complexity and significantly improves overall system resilience. A production-ready system requires meticulous error handling. Implement a try-except block specifically targeting JSON decoder error and Pydantic validation error. If a parsing error occurs, log the raw unparsed LLM output immediately, along with the specific exception traceback for later analysis and debugging. The fallback strategy must prevent application failure. Options include defaulting to a predefined safe JSON structure, returning a specific error code to the client, or triggering the self-correction loop. Never allow unvalidated LLM output to proceed into the core application logic. Selecting the constraint method depends on system requirements. For high-throughput, general reliability, native API JSON mode coupled with Pydantic validation offers the optimal balance of speed and compliance. If you are using an open-source model or require absolute guaranteed structural integrity, token-level force decoding is necessary, accepting the increased latency. Always treat the LLM output as untrusted external input until it has successfully passed schema validation. Integrating these specific hands-on techniques ensures your LLM-powered systems deliver reliable, structured data ready for immediate application consumption.